Okay, so in our last video we learned one reaction for radicals, and we mostly spent some time looking at the mechanisms for radicals, and I talked a little bit about the ozone layer and stuff. Hopefully that wasn't too much of a distraction. In this video we're going to just go through uh, a bunch of different reactions, and I'm not going to make you guys learn a whole bunch of mechanisms here. The mechanisms are really similar to the first one that I showed you. But these radical mechanisms are sort of orthogonal to a lot of the other stuff you'll learn. And so, there's not a lot of like pattern type stuff you can extract from it. It more just becomes sort of a memorization thing. And it doesn't really help you that much in the normal course. In a course where I'm letting you do open notebook and stuff, there it's even less utility. So I'm definitely not going to make you guys kind of struggle through that. Let's look at some other reactions. So all of these reactions, the main thing to know about the mechanism is they're fundamentally happening in a very different way from the other reactions we learned for alkenes. And that doesn't just apply to the one I'm about to show you for an alkene, that's just all of these. So these are radical mechanisms. They're different from other mechanisms that we'll learn in this course. Okay, so we know that if we take this and we subject it to HBr, the product that we'll get out of it is this. This is an addition reaction. But what if we don't want to do that? So that's Markovnikov addition. And if you remember for alcohols, right, we have a Markovnikov addition, and then we also have another method for making alcohols that's anti-Markovnikov. We may want to actually add Br in the anti-Markovnikov position. And so chemists have a strategy for doing that. And we take HBr and peroxides. And because this goes through a radical mechanism, we can get different selectivity here. I said I wasn't going to make you guys learn any more mechanisms, but this one's kind of interesting to just look at. So yeah, let's just very quickly look at this one. So the initiation step for peroxides, you can actually break these down with heat. So if you have a bottle of hydrogen peroxide at home, this is probably what's happening as it slowly decomposes. If I just put some heat in there, it'll break up homolytically, into this. So now I have this really reactive oxygen species. And then the next step, what happens is this reacts with the HBr. And so what I get out of this is, in this case, water. But also I get Br dot, so this highly reactive bromine species. And now this would be in this particular case our initiation steps. So we have two parts to the initiation. You don't really end up in the propagation part of the mechanism until you start to react with the substrate. So once the substrate enters into the equation, that's the start of the propagation step. But let's take a look at what the propagation step looks like here. So in the first step, I form a radical. And that radical goes here. And the bromine goes there. So when you're doing, when you're looking at the HBr mechanism, so I'm going to call this propagation. I'm not going to take you through the rest of the steps. You're welcome to look those up. But yeah, this keeps going, and eventually you get to your product, and then the termination steps or whatever. But the key thing in terms of looking at the radioselectivity for this reaction, why does this go anti-Markovnikov? You're still forming the most stable radical. Just like in the carbocation reaction, which I'll draw right below it, in our first step, yeah, we're forming the most stable carbocation. The difference between these two reactions, even though both of them are sort of following the same trend, you're forming the most stable species, is that in the first step of the alkene HBr addition, you're adding the hydrogen first. So when you form the carbocation, yeah, it goes on the most stable carbon, but because your hydrogen is the first thing to react, ultimately bromide gets to come in and substitute at that carbocation. If you look up here at the top, though, in the propagation step, or the beginning of the propagation steps, I guess I should say, for the radical one, the first step is you form a bond to the Br. Okay? So you're still forming this most stable radical, but because you formed the bond to the Br first, the Br bond actually forms on the more substituted carbon. So the underlying sort of principle that guides Markovnikov and anti-Markovnikov addition, it's the same. It all kind of revolves around reactivity and thermodynamics and stability and stuff. It's just the way that we name the products is different, right? The atoms are always going to follow whatever the lowest energy pathway is. What we see in the end, the radioselectivity, and what we consider useful as humans, we have names for. But there's nothing fundamentally different happening here thermodynamically. What's different on a fundamental level is the mechanism for this has now changed. And by changing the mechanism for these reactions, we are given different regioselectivity. So this is just for comparison. Compare with the mechanism when we use peroxides. Okay? So you just want to compare that with the other mechanism. And that's really the main thing. So if you see something different, if the product is different, that means that you're in especially for this reaction where we're looking at like both of these reactions have HBr, they're both on identical substrates. In one of them, we've just added peroxides, but we're getting this radically different selectivity for it. What that means is that you must be going through a different mechanism, right? And in this case, we can see that because these are well-studied reactions. We're going through a radical mechanism that's what's allowing us to get at this anti-Markovnikov reaction. So here, if I'm trying to put this in my deck of flashcards, I'm going from an alkene to an alkyl I can do this, halide. And then I would want to note that this goes anti-Markovnikov. And that's really useful because sometimes you might want to get the bromine on the end, right? Like if I wanted to do, one of the reactions that the carbon-carbon bond forming reaction, you want to have the bromine on a primary carbon. So this would be really useful for that reaction where we deprotonate the alkyne and then try to alkylate it, right? Because that's typically you're trying to get the halogen on the less substituted carbon atom. We'll work through, if that didn't make any sense to you, don't worry about it. We'll work through that in some synthesis problems. All right, for real, I won't give you guys any more mechanisms. But it is useful to just kind of take a look and compare to understand like how you're kind of changing the selectivity here. Okay, so the next one, reaction, and this one I definitely am not showing you the mechanism for. We can do allylic bromination. And to do that, we use something called NBS. So NBS looks like this. Sometimes you'll see it drawn out entirely. And then other times you'll see it just written as NBS. So if you take NBS and you heat this reaction up, what you get out of it is substitution at the allylic position. So the allylic position is here. So the allylic position is once removed from the double bond. So remember that we also have hydrogens. I'm going to change color for the pen here. We have this hydrogen here. This is the vinylic position. The allylic position are hydrogens that are attached to the carbon that's attached to the double bond. I know that's kind of hard to imagine because it's like attached to the attached to the attached to the. But if you go, if you're looking directly at the double bond here and you go one carbon over from it, that is where all the allylic positions are. So that's an allylic carbon in any of the hydrogens or other substitutions on there. So for example, over here would be considered allylic themselves. Just like a primary carbon has primary hydrogens, an allylic carbon has allylic substituents on it. So, yeah, what would we put in our deck here? We would say alkene, maybe. So this is, I don't know how you want to qualify this in the notes, but obviously there has to be an allylic position for this reaction to work. Alkene to allyl bromide. Alkene to an allyl bromide. And again, this is a pretty useful reaction. So these are not one-off. Some of the reactions we learn you'll find you don't really use that much. This is definitely one that's super useful. Anytime you can take and add a halogen into a molecule selectively, you probably have a pretty useful reaction for it. And we'll see why that is when we get to our chapter on nucleophilic substitution. But yep, alkene to allyl bromide. Yeah, I guess one note about. Actually, let's hold off on that. I guess one thing I'll say is if you try and do this reaction, let's say you try and just take and use Br2 in light, this reaction doesn't go. Or at least it doesn't give you what you want. So you're not going to get this. What you'll actually end up seeing is the addition product that we see for Br2 because it's faster than the radical reaction would be there. So this doesn't work. So just note that that's not a good strategy. If you're using the allyl, if you're trying to substitute at the allylic position, you have to use this special reagent called NBS. And you can look at the mechanism to try and parse why that is. I would recommend that you do that because it's kind of, when you're learning organic chemistry, if you really want to understand what you're doing, you have to understand the mechanisms. But instead of just sort of brute force memorizing the mechanism, I would take it and look at and try and understand what the hell is going on there. Why do we use NBS and not Br2? And I think our textbook, the Anselm textbook, does a pretty good job of explaining that. But it is confusing. And I know from experience just teaching this class that when I've taught the mechanism, a very small percentage of the students actually understand what the rationale is behind it, even though a large percentage of you guys can memorize it and turn it out on the test. So take the opportunity. I know we're in this weird quarantine study time, but take the opportunity to try and really kind of learn this stuff in a deeper way than you really get the opportunity to do with all the different types of tests we give you. Let's see. Yeah, I think that's all of our reactions that we have. So we learned 3 reactions here. Learn this. If we take this and we add Br2, we'll get Br. So this allowed us to take an alkane and convert it to an alkyl halide. Very useful. This, if we take HBr and we take peroxides, we can get an alkyl halide at the less substituted position. So we can take an alkene, and we have even more control over what the alkene chemistry is. We can take an alkene and we can go to an alkyl halide but we can do that Antimarkovnikov. I'm just going to substitute that guy's name. We're going to call him Mark. And then the last thing we learned was that if we want to actually substitute at the allylic position, let me make this, let's see, I don't want it to look identical to the one above. Oh, no, we won't, okay. If I want to substitute at the allylic position but leave that alkene intact, for example, I could do NBS. So that allows me to go from an alkene to an allyl halide. Okay. So one note about all these reactions is the radioselectivity is very good for bromine. But not good for chlorine. So a lot of times when I'm doing these reactions, like when we're doing alkene additions, I just use bromine, but you could conceivably use chlorine. In this particular case, chlorine is not a viable option, and that's because your radioselectivity is not good when you use chlorine. And this comes from some physical chemistry, or some ideas around physical chemistry, called, the main thing that it hinges on is called Hammonds postulate. And so if you want to understand chemical reactivity, a lot of what you have to think about is the transition state. And these things are short-lived, and so Hammonds postulate allows us to get at what the transition state might look like. So I'll take you through the Hammonds postulate really quick. It's a really useful lens for looking at chemical reactions in general, and we teach it specifically in this radical portion. But it's applicable to things that we've already learned and things that we'll learn in the future. If you look at just any reaction plot, we've got this transition state that's up at the top. Let's just call it some transient species. So let's say you're taking something and you're taking A and B and you're mixing them together and you're trying to form a bond between them. So A and B are just imaginary atoms. So I'm trying to form AB. So this is our products. Thank you. Very helpful, iPad. Okay. These are our products down here. And these are our reactants, naturally. And then over here we have, energy, potential energy, something like that. And then this is our reaction coordinate down here, just meaning that as we move to the right, we're moving like further forward from the reactant to the product. It's kind of like, although it's not exactly, like looking at the time of the reaction, right? So in the beginning of the reaction, you have reactants, and at the end of the reaction, you have products. You start a reaction to the finish reaction. So it's not exactly time, but you kind of think about it like that. All right, so anyway, so I've got this transition state. I'm going from my reactants to my products. All Hammonds postulate says is that the transition state is going to resemble how can I phrase this? It's going to resemble let's say it's going to resemble the reactants and the products. So let's just start there. Okay, that's not exactly what Hammond's postulate is, but let's just use that as our starting point. We know that if you're taking A and B and you're going and you're forming a bond between them, so initially there's no bond, and at the end there is a bond, that in between there you're going to have like a partial bond formed. And that's really what we're trying to show up here with this transition state. We're saying, well, the bond's not quite formed yet. So we can't say, okay, it is actually the product, but it's also not formed, right? Those things are starting to interact, and we have this really high energy species. So yeah, we don't really know what that transition state looks like. It only exists for about a femtosecond. But we know that it probably, or it must look something like the products and something like the reactants. You know, it's just like when two parents have a kid, you expect the kid to look something like the parents. And that's what we're saying here. We're saying that, you know, if we have reactants, we have products, the transition state's going to look like something, some chimeric version of those two. What Hammond's postulate says that's really useful is that the transition state resembles whichever let's say resembles more of the species that it is closer to in potential energy. Okay, so let's go back over here and look at this. If we look at our reactants and their potential energy, and then we look at our products down here and its potential energy, which of these are closer in energy to, clean this up a little bit, draw more in here. Sorry, I'm not trying to make you guys nauseated. And right at the crux of like a very complicated explanation too. All right, yeah, if we look at this, we've got our reactants over here, and we're saying, well, you know, which of these is it closer to in energy? So this is our potential energy for our transition state. It's way up here, right? So our potential energy is increasing. Here is our potential energy for our reactants. And then here is our potential energy for our products. Okay, so what is the transition state closer to? You know, there's nothing tricky about this. The transition state is closer in energy to the reactants than the products. I mean, the products are like way down here, and the transition state is way up here. So reactants are higher in energy, and so naturally they're closer to the transition state. And so that's really what Hammond's postulate is saying. It's saying, well, if I have this really high energy transition state, whatever is higher in energy, the reactants or the products or intermediates or whatever you're looking at, that's what it's going to resemble the most. Okay, and so what you'll see is this condensed down into a form that says, for an endothermic reaction, this is another way to state the same exact thing that I just said. For an endothermic reaction, or I guess what I should be saying is endergonic. An endergonic reaction. The transition state resembles the products. And so remember, that's a reaction energy diagram where things look like this. So I've got my potential energy over here. If it's endergonic, it's going to look like this. I've got my reactants here. I've got my products up here. I've got my transition state up here. You can see that the transition state, which is right here, is closer in energy. It's closer in potential energy to the products than it is to the reactants. So that makes sense in the context of what I just said. if we look at for an exergonic reaction, the transition state resembles the reactants, and this is where we started. So this corollary that you would expect to hold, in fact, does hold. If I'm looking at something like this, so now I'm looking at reactants and products, I see that the reactants now are closer to the transition state and potential energy than they are to the products. So this distance is much greater than this distance. And so because the distance in potential energy between the transition state and the reactants is shorter, we expect that the transition state is going to look more like the reactants than it will the product. So in my parent-child analogy, this is where the transition, one parent has a lot of dominant genes, and so the kid looks just like that parent and not a lot like the other parent. And so in this case, that parent with the dominant genes is going to be the reactant, and the parent who the baby looks nothing like is going to be the products, right? So that's what we're thinking about with the transition state. We're just saying, well, it's got to look like one of them. It's going to look more like the one that it's closer to in potential energy than the other. That's the entirety of the Hammonds postulate. So, most of the time I think when students are trying to memorize it, it's like, yeah, you're trying to memorize all this other crap, so you're just kind of like, all right, I'm going to memorize these two little axioms here. But you can actually kind of reason this through on first principles, right? If this was a physical chemistry class, there'd be all this horrible math attached to it, but it's not. It's an organic chemistry class, so we have just some pictures to look at. All right, so what the hell does this have to do with radicals? So in the radical reaction that we looked at earlier, if we use bromine, I'm sorry, this video is getting a little long. If we use bromine here, in the first step, let's say it's, all right, so I've done the initiation step. Now I'm looking at the radical bromine, and it's going to combine with my substrate. I have two different intermediates that I'm going to form here. I can form this, which is going to be higher in energy than this. Okay? Let me get rid of these hydrogens. I think they actually cause more confusion than they should. But so I have two radicals I could form here. I'm starting with my reactants, which are down here. So I've got my potential energy plot over here. And so we're looking at these intermediates here because that's the important thing. So I can either go here or I can go here. And then I go down to my products. When I go down to my products, let's see, am I worried about my products here? Oh, I see what my problem is. Derp. Yeah, it helps when you're talking about transition states if you actually draw out the transition states. Okay, so I have one product at the top, right? So this is our high energy guy. Then I have a different product here. This is our low energy intermediate. And so if we're trying to look at selectivity through the eyes of sort of separation in and the intermediates here, separation in energy. So, we need some separation in the energy here. There's a potential energy difference between these. Then this might be what it looks like. So if I'm starting down here and I'm trying to kind of go to this high energy species, you can see that it's going to take a lot more energy for me to get up here and form that high energy species, and that the lower reaction barrier is to get to the low energy species here. And so, these things, the transition states or whatever, correspond to the activation energy and relate back to the rate of the reaction. So the low energy species forms a lot faster than the high energy species. And relating it back to the Hammond postulate, we can see that the transition state, because this step in the reaction is endergonic, the transition state resembles our products. So I'm using product here to refer to this intermediate. We're not talking about the actual product that you ultimately form. That's not actually important for how this reaction, how the selectivity in this reaction works. But the transition state resembles our products. And because our products have a very high and a very low energy, there's actual separation between them. So you can guide the reaction towards the low energy one as opposed to the high energy one. Now, if we look at chlorine, we look at a diagram for chlorine, so we've got a potential energy. Again, we have a reaction coordinate. Everything is the same. The only thing that we're changing here is now we're going to put in chlorine dot. So the difference between chlorine and bromine is that chlorine is actually much less stable. So it's a higher energy radical. And the result of this is that it raises the potential energy of the starting material to where now the starting material is much closer to the transition state than the radical product. So you still have radical products that are well differentiated. The potential energy difference in the product doesn't change. Or at least we can assume it doesn't change that much. Okay. So I've got this, which I'm forming, which is the higher potential energy species, and I've got this one, which we know is the lower energy species. But you'll notice that now the way I've drawn them, oh my goodness. Sorry, y'all, I need to go to art school. Now the way I've drawn them, what we see is that the reaction is no longer endergonic, it's now exergonic. So now our transition state resembles the reactants. And this eliminates all of our selectivity because the reactants aren't, there's no differentiation within the reactants. All I'm looking at for the reactants, they have a chlorine radical. Here I'm looking at these two products, right? That's where I need to, if I want to form one versus the other, the transition state has to be separated further along. If it's separates, if your transition state occurs too early or too close to the reactants, now I just don't see a huge difference in the transition state. So the potential energy difference here is small. So in this case, our parents, if we're thinking back to that parent analogy, the parent that dominates genetically is going to be the one with the chlorine radical, and then, these parents over here, the transition state doesn't really look like them. And if we were trying to separate the energy, if we're trying to get rate differences, I guess I'd say, between the formation of one of these versus the other, we're trying to get that potential energy gap to be matched up here in the transition state. So we get this up here. We want this potential energy gap to be matched up here. if the transition state looks just like the reactants, well, then we're not going to see that because these are the reactants. There is no separation in energy between them. It's the same thing, right? These are all the same things. We need it to look like the products so that we can actually start to see that separation in energy. And if we come back up here to the one with bromine, where things are endergonic, now what we see is, okay, the reactants don't look a lot like our transition state. The transition state, in fact, does look like our products. And so the potential energy gap between the products starts to match the potential energy gap between the transition state. So I know this is really heady, but that's sort of the thrust of it, right? If you want to have another way to say it, a much simpler way to say it, and I encourage you to kind of read up on this and read the textbook. This is a hard thing to explain and a hard thing to kind of wrap your head around in like 5-10 minutes of a video lecture. The general takeaway from Hammonds' postulate is that more reactive starting materials, or more reactive, let's just say more reactive reactants, and that includes like reagents and substrates or whatever, have less selectivity. And I'm actually going to change that. Let's just say, for our sake, more reactive reagents have less selectivity. That's really what we're kind of getting at here. And the underlying reason for that is that if the reagents are really reactive, then the transition state won't resemble the products. And so even if there is a potential energy difference in the products, you won't see that potential energy difference in the transition state. In order to see that, the transition state has to actually resemble the products. So if it just resembles the reagents, there's no separation in the potential energy there, and you just kind of get a mixture of crap. So if you try and run this reaction practically with Cl2, you're not going to see any kind of really clean reaction. You might get some extra gearing of that, but you're also going to see a lot of this, right? You're going to see, I don't know what the actual percentage is, but you're going to see equal amounts of that. So you have to use, practically speaking, in the lab, you use bromine to do these types of reactions. From an impractical, just trying to look at the mechanism thing, you have to kind of understand Hammonds' postulate to see why that is. But more reactive reagents have less selectivity. That should make sense to you on some level, right? The more reactive something is, the less it cares what it reacts with. It's just super high energy. Less reactive things have more selectivity. Yep. Okay. So before I end this lecture, the key takeaway here, because I know we've gone down this rabbit hole on Hammonds' postulate, and this is not me going down any kind of weird rabbit hole. This is standard stuff that we teach in this course. But the very, very key things for you to understand, for this class going forward and for the second course is definitely know these reactions, right? Maybe understand the reaction mechanisms a good bit. If you really want to kind of get a deeper look into chemical reactivity in general, Hammonds' postulate is really good for that. It might seem overwhelming right now, but it's not crazy or anything. You guys are all more capable enough of understanding that. But the main thing you have to remember, carrying this step forward to the second course, are the reactions. That's what usually gets students, especially for this chapter. So file those away somewhere.